So hello friends, welcome back to our channel STM Mechatronics. So in this video we are going to see some new modifications that we have done in our existing code in order to improve the readability and the functionality. So first I'll build my code. I'll load this new code into our controller and see the working. So TFT display, today is 1st of March 2026. I'll load this code. And as you can see, the existing functionality is retained, right? So first the black color is displayed filled in the display, then the white color is filled, then we have some lines drawn on the display. Now we'll see there are two different lines starting from the two different positions, right? So we will see how we have achieved that. Again, in this new code, I have added some mathematical function to draw the lines. So we will see how the code works using the mathematical functions. Okay, so the main.c is as it is. We have not modified any code in the main.c. Okay, apart from this display image 2 function that we have added. So everything, rest of things are same. In display.c, right, we have added one new function at the end of the file, right? This is the display image 2 function. I'll walk you through this function. We have modified this function that was our existing function, this display.c, right, display image function. We have copied this function and we have modified this function. So I'll walk you through that function, and again we have modified some part of the code, existing code, right? So what we have changed, I'll tell you about it, and how we have implemented this line drawing, I'll explain that to you. So first walk you through the display.h, right? We have added few macros basically for the bits position, port bits position. Okay, so we are currently using the port B for chip select, reset, SDO, clock, data and command lines. So these are connected on various different lines. So as you can see, reset is connected on PB0, CS is connected on PB1, SDO is connected to PB5, SCK is connected to PB3, and data and command is connected to PB4. So in order to set or reset this bit, right, what we have to do is set the particular bit. So if I want to set the PB0 port pin, right, I have to write 1 on the PB0, right? This is the 0th position. So I'll have to write 1 over here on the 0th position in order to make the PB0 bit as set, right? For PB1, what I'll have to do is I'll have to take the 1 and shift it to 1, shift it by left by 1, right? So this PB1 will get set. In order to set PB2, what I'll have to take, I'll have to take 0x01, which will be over here, and I'll have to shift it by 2, right? Left shift it by 2 so that PB2 will get set, right? And by default, while shifting to the left, 0 is appended on the right side, that we know. Okay, so likewise we have added these macros. We can go on adding the next macros for PB10, PB11, PB12, PB13, PB14 and PB15, but we have not used up to PB15 in our code. That's why I have left it to PB9. You can go and add it over here. Now here you can see that I have added this display image 2 declaration, function declaration, and give clock pulse function declaration. Now you will see what we have changed in our code. Now in the previous code, we have used this send command and send data functions. So when we want to send the command to the display, right, we were using this send command function and we were giving the command code to it. Now what used to happen is, if you want to set the GPIO bit 5, right, that is connected to SDO, right, what we have to set shift 1 by 5 times, right? Left shift it by 5 times, so that the BSRR bit for PB5 will get set. So we have defined simply a micro for that, right? So whenever I want to set the PB5, I can directly write it as PB5, right? And I can assign that value to BSRR, GPIO-B BSRR register, right? Now if I want to clear that bit, what I have to use is PB5 value is like all the bits are 0, 0, 0, 1, 0, right? And 0, 0, 0, 0. Now I have to clear that bit. So what I'll do is I'll take the negate of it, inverse of it. So all those bits will set to 1. Only the PB5 bit, that is bit number 5, fifth on the fifth position, right? That will get reset. That is set to logic 0. And rest of the bits will be 1, 1, 1, 1. Okay, so that value I'll assign it to BSRR. First I'll AND it and give that value to BSRR, right? Now bit set reset register. So in order to reset that, right, what I have to do is again I have to shift that same bit by 16 times. So 0 to 15 bits are used for set and 16 to 31 bits are used for reset. So what I have done is I have used that micro, PB5 micro, left shifted it by 16 times. So that reset bit for PB5 gets set. Okay. So this is one simple modification that we have done, but it has improved the readability of the code on a large scale. Okay. So it made the code very simple, easy to read. Okay. Now next thing was what we had done is here what we had done earlier, like we used to set that clock bit, then give some delay, then reset it and give some delay. Okay. Now we have written one function, right? Now I'll walk you to that function. Give clock pulse, right? We have made it inline. Now this inline keyword, what it does is like it places this whole code wherever this function is called. So give clock, wherever give clock pulse is called, these 5 lines will be put there. Okay. So your code readability is increased, but your code size will increase at the compile time. Okay. So in give clock pulse, what we have done is like we have used the same principle, like we have used PB3 micro. First we are setting that bit, okay, then we are giving two NOP instructions, no operation. So this is a simple delay. Then we are again clearing that bit and we are resetting it. So this is one simple thing. Okay, this is very simple logic. Now in data we have used the same thing. Okay, instead of writing it as 0x1000 or 0x20, right, and assigning that value to BSRR register of GPIO port B, we have made that macro and write it over here. So this has improved the readability of the code. And again, by making this give clock pulse function as inline, the code speed is improved, code size will be increased, that is a drawback, but your code readability is improved, the speed is improved. Now coming to the disp image 2 function, right? So at the start of this video I have told you that we have used the mathematical function for line draw, right? So the mathematical function for line is y equals to mx plus c, where y is the y coordinate, m is the slope, x is the x coordinate and c is the offset, right? So y is the column coordinate, x is the row coordinate, m is the slope and c is the offset. This is the mathematical function that we are going to use, y equals to mx plus c, right? So I'll compare these two functions. Here you can see that, right, we are setting the chip select, right, we are setting the data or command pin, then we are doing some complex operations over here, right? We are checking like there are multiple conditions that we are checking, then we are taking action according to whether to display the red pixel or not, or we want to display all white pixel, right? So what we have done over here is in display image 2, so we have taken the endpoints for row index and column index. That is, for row index it is 131 and for column index it is 161, or the opposite. Now what we have done is we want to calculate the slope. So what we have done is 131 divided by 161, right? That will give us the slope of the line, right? Now what we want to do is, again we are taking some different slope, right? We want to take the half, right? So I'll show it to you. What I mean is, so here this will be the start point and this will be the end point, right? So for first slope it is like 131 161, right? That will be the case. And so you can see this second line, it is drawn from certain offset and it goes till the mid of the display. Not exactly mid, it is offsetted by some certain value, right? But the slope of the line is reduced, right? Here the slope of the line is, you can see that slope of the line, right? So we have two different slope of the lines. So what we have done is we have taken like 131 divided by 2, it gives us the mid, right, mid of the column, and we have divided it by x, so that gives us the slope, right? Now y1 and y2, these are the 2 points, right? So we know like x value, then we know the slope value, so we can get the y value. So for like you can see that for certain offset, for first line we have taken the offset as 0, for second line we have taken the offset as 10. Okay, so if I change this offset to 0, right, build the code, you can see that, right, this is the middle of the display. Earlier the second line was starting from over here, that is 10 offset. Now it will start from the 0 offset and it will go till the mid of the display, right? It has started from the same origin point, that is 0x00, and you can see it comes exactly to the center of the display, exactly half of the display, right? Not the center, but like this row position, half of the row, right? Okay, so that we have achieved using this y equals to mx line equation, right? Now what we want to do is we want to iterate for 162 times, because we have total 162 rows. Okay, now we are getting the y values using the line equation. Okay, so we know the slope, we know x coordinate because we are iterating through the rows, and we know the offset. Same goes for y2, that is line 2. Okay, now if y, like we are going through the column, each column, right? So if y equals to 0, y is less than 132, then y plus plus. Okay, so this x equals to 0 and y equals to 0, then display the red pixel. That is simple thing. Okay, so if x equals to 0, y equals to 0, mark it as red. So we are marking that boundary as red. We can add one more condition, that if x equals to let's suppose 131 or 161 and y equals to 131, it will give us the border. So we'll add that over here also. So that will give us the border. This will give us the 131, right? That will give us the border. So display red pixel over the border. If y equals to y1, So from this first equation we got the y coordinate, right? If the y, we are while iterating through the column, right? If y1 equals to y, or y equals to y1, or y equals to y2, then mark that pixel as red, else mark the pixel as white, right? So this will mark the coordinates of the line. We can do something like this also, like else if we want to mark the two lines as on the like two different colors, right? So what we will do is we'll keep this x, we'll mark this y, right? Now instead of pixel red, what we will do is red, green and blue. So we'll build this. So what we have done is, like, if first equation is true, y is equals to first equation, then mark that line as red. If y equals to second equation, mark that line as green. Now you can see that, right? We have modified our code. So earlier we used to only see that this line was red, this line was red, this line was red, this line was not red, this line was white, right? This line was white. Then this second line was also red. Now we have changed the color of the line and we have marked the border also. Okay, so these modifications we have made in our code. So these are very simple modifications, right? This is very simple. You can go on add like more slope or more line equations, more slope, right? So likewise you can modify your code. Now what we can do is, right, here you can see that, like, in the send data, right, in send data, like this is GPIO B, right? Again this is B, port B, right? This is port B, this is GPIO 4, right? And display data, mark it as 1. So what we can do is, instead of these, right, making display as 1, so we know that GPIO B bit set reset, right, or with this is GPIO 4, right? So we will use PB4. PB4, right? So we will make our code like this. Now here chip select reset, right, display image. Here over here it is set, right, display image. So what we can do is, if it is set, then we can write that. If it is reset, we can write that function. Okay. Okay. So we can modify these functions as well. So this will improve the speed of the project or speed of the code. First we will check by this simple modification our code works perfectly or not. So there should be no problem, right? Yeah. So there is no problem in our code. It works perfectly fine. I'm not explaining the previous code because it is well explained in the previous videos also. Okay. Yeah. So what we will do is, we have changed this one line of code, right? Again PB4, right? Over here what we have to do is, PB4, we have to left shift it by 16, right? So this will reset it, and we have to clear the PB4, right? So over here we have to ampersand and negate to that. Okay, so this will clear the PB4. Okay, now improve. The speed has increased. And our code works perfectly fine even after this modification, right? So here you can see that the border is marked with the red color, right? We can change the color of the border. So in display image 2, right? In display image 2, what we will do is we will mark the border color as blue. Over here it is pixel is red, but what we are doing is, this is for first byte is for red, second byte is for green, and third byte is for blue pixel. Okay, do one more thing. Now we have changed only one function, right? So display image, set top to bottom, set color, we'll do okay. Now what we'll do is, instead of screen color as 0x00 0xFFFF, we'll mark it as 0, so it will give us a black color on the display. Starting from white. Right. Now over here you can see the border is marked with blue color. First line is of red, second line is of green color, right? With the origin at 00, the endpoint is like 131, 161, and for the green line it is like 161. That is the row. This is 161, and the column is like half of the 131. Okay. So, like we have modified our code, we have made it simple, right? We have made it readable. Now all these functions like HAL GPIO write pin, read pin, you can directly replace it by GPIO BSRR, because we know that all these port pins are connected to GPIO B. If it has been used on other, like we have to use that GPIO A or GPIO C accordingly, right? But as we know, it is fixed to port B, so we can directly write it as GPIO port B set, right? GPIO B bit set reset. Now we want to set that chip select, SPI pin chip select. It is PB1, right? So we can use it PB1, and and we can comment this set, right? Now I know it is like reset, so what we can do is we can copy this, paste it over here, change it, make it this, right? Now left shift by 16, so it will reset that bit. Okay, so it will reset that bit. So what I will do is I'll go over here and make it this, right? Again, this is command and data pin. So command and data pin, right? This is chip select, reset. You can go directly in the command and data pin, right? Data and command pin, send data. Display data, for display data we are writing one. Okay. We can confirm it. PB4 data and command, data and command. So data and command is connected to PB4, so that's why we have replaced it with BSRR PB4. Okay. Send command, we will go inside the send command, right? Q clock pulse, shift bits, video clock pulse and shift bits. So like this display is done, completed within like 11 seconds, right? Again, now we have like used the bare metal programming, so the code is written in bare metal programming. Also we have used the GPIO bit banging in order to achieve the SPI functionality. We have not used the SPI register or SPI functionality of STM32 controller, right? So in next video what we can do is we can use the SPI functionality or SPI peripheral of the STM32 and achieve the same thing, right? So that we will see in the next video. Thanks for watching this video. So if you enjoy this video, if you learned from this video, give it a likes, share with your friends, and thanks for watching. We will see you in the next video.